So today we'll talk about matrix concentration. So inequalities on the spectral norm of random matrices. So before we get into matrices, let me recall the Bernstein's inequality, right, for scalars. And then I'll talk a little bit about what we're going to say for matrices and why it will matter and how it is extension, just an extension of the scalar Bernstein in a way. Right? So let's recall Bernstein's inequality. Right, so the scalar version. Okay, so what it said, make sure I use exactly the formulation that we had. So it said that if we had, x1 through xn, just random variables, right, independent, right, and scalars, scalar random variables, right, then we have the following. The conditions we had on them was that they were centered. We had a control under their variance, and we had that they were bounded, right? So we'll say that xi is bounded by a almost surely, right? So its probability 1 is smaller than a for all I, right? We'll also say the expected value of xi is 0, right? So they're bounded, they're centered, and we put their mean being, right, their variance as being sigma squared. Okay, and then the inequality controls the deviations or the tails of the sum of these random variables, right? So control the probability. That's the spectral norm, the sum of x size, I from 1 to n, where this was bigger than some t, was smaller or equal than 2 times the exponential of. Right, so this is exactly what we saw a few weeks ago. 2n sigma squared plus 2/3 a t. Okay, so this is the inequality we saw a few weeks ago, right? To control this, we had a control on the tail of sums of random variables, and we're going to show exactly the same thing for matrices. Right now, of course, for matrices, one thing we could do, of course, is we could just say, well, it's, if I have now a bunch of matrices, so now we're going to have the matrix, right? Matrix Bernstein inequality. Right, and our objects will be symmetric matrices. It will be x1 through xn will be symmetric matrices. Right, what I mean by symmetric is that xi is equal to xi transpose. Not symmetric is in a random variable being symmetric, having the same distribution as minus the random variable, right? Here, I mean, they are symmetric in the sense. So d by d. Right, and what we want to control actually is the largest eigenvalue of the sum. Right, so we'll have similar quantities as before, right? So similar conditions. So we'll ask that they're centered. We'll ask that the expectation of xi is 0. Right? We'll ask that now they're bounded. We'll ask that the maximum eigenvalue of the xi's are bounded by the quantity r. And we'll have a slightly different definition for variance. Variance will be here, will be the sum, will be the spectral norm of the sum of the expected value of the xi squared. Okay, but similar, they're centered, they're bounded, and there's some variance parameter, which, right, so here I'm summing over n things, so this variance parameter is like n times bigger than this one. Okay. And now what we want to control is we want to control the probability, right, that the sum of all these random variables, I1 through n of xi, that the maximum eigenvalue is this. So let me write that. Maximum eigenvalue of bigger than t. We want to control this to be small or equal than something. Okay, and I'll write that something in a second. But before that, let me just say a few words, right? So, of course, we could just use normal Bernstein and say, well, the entries, this will be true for all the, the entries of the matrix themselves will be centered, right? This can also give some bound on the entry, right? And this will give some bound on the variance of the entries as well, right? So we could just use the Bernstein's inequality per entry on every entry of the matrix and get a bound there and then transform it into a bound on the spectral norm, right? But of course, bounding entries with spectral norm and vice versa, right? If we use, say, a bound on the entries to get a bound on the spectral norm and then a bound on the entries or vice versa, right? The loss is incredible, right? We lose a lot. We lose the polynomial factors in the dimension for sure, right? And there's going to be many, many instances in which the type of thing we want to control, like if you think of some kind of error, or you want to control the size of something random, the size of these things will be actually matrices, and we'll be interested in the spectral norm. Think, for example, back to the spike model and the VAP transition stuff, right? So we had, if we think of the spike as a signal and the Gaussian matrix, say, as noise, then really what we want to do is if we want to say that the noise doesn't affect the signal so much, really the right way of measuring this is in spectral norm. We want to make sure that the spectral norm of the noise doesn't affect the signal. And this is how we're going to be able to say, for example, that spectral clustering works well on average, or that certain algorithms work well because the way the error, or the way that sort of the perturbations they have for them not to just be working directly on the signal are spectral perturbations, are noise that you should really measure in the spectral sense, and so this is the right quantity to control. Right, so now, further ado, when we write the inequality, so we get d exponential of, and then it's exactly the same. Right. And the striking thing is that this inequality is essentially exactly the same. Right? So basically we have, what are the differences? So of course there's an n here that is not over here, but that's because this variance is being defined as a sum, right? So there's sort of an n already here, right? So this is really, this term really is sort of the analog to this one, right? And then everything else is sort of the same, right? The two that we have here is because we're controlling here both sides, the probability of being too big and too small. Here we're just controlling one of them, so the two wouldn't belong. Now what we get here is this dimensional factor d. It turns out this will be important, right? If you think about how does this make a difference on what's the typical size of this random variable, and if you think about it, right, like if you look at the change of variables on t, to make the d go away, you need something like square root log d, right? So that here you pick up an x plus minus log d that cancels out this d, and then you would roughly need something like this. And we'll see that oftentimes these inequalities do lose by that logarithmic factor. So this is an issue that sometimes one needs to work hard to improve in particular examples. But in general, this inequality is able to do a lot. Like if you need to control the error, and the error is somehow spectral, this, just like scalar Bernstein works for almost everything, this works for almost any type of spectral problem you might have. Okay? And so in this class, actually, I will not prove this, although I'll give references for the proof of this, and instead we'll prove a lot of matrix concentration inequalities, actually not by controlling the probability that this deviation is very large, but instead by controlling the expected value of things like lambda max of W, of a random matrix, say X, right, where X is a random matrix, or expected value of the spectral norm. Right, so instead of controlling tails, we'll control the typical size of this. And then going from the typical size to tails will actually be quite easy, right, because these are already very high-dimensional objects, so they concentrate very, very well by themselves. And the reason why sort of tails here are not maybe as important is that the tails are very important in the other cases because you're going to have to union bound a lot. And usually over matrices, we don't have to union bound as much. But so what I'm going to do next is I'm going to show you how you can go from controls on expected value into tails, and then we'll spend the rest of the lecture essentially working with controlling expected values of this form. In order to move from controlling expected values of spectral norms to tails, what we'll use is concentration. So the idea being that these objects, they already concentrate well by themselves, as we'll see. And so let me start by giving a notion of concentration, and then we'll use Avignon matrices to show how this could be used, and this essentially can be used in general. All right, so this is the notion of Gaussian concentration. Okay, so Gaussian concentration is a theorem, and it's about whether about how high-dimensional objects do tend to concentrate around their means. In particular, it's about how high-dimensional functions that are very stable with respect to the input, that they concentrate well. So let's say we have a function n going from Rn to R. And Gaussian concentration will say that if G is a Gaussian random variable, right, so just a vector with n IID Gaussians, what Gaussian concentration will say is that Fg concentrates well around its mean. Right, but now, of course, we can come up with crazy functions that don't concentrate well, right? So what we'll ask of f is that f is stable with respect to the input. So f is somehow stable with respect to input. Right? The idea being that if f doesn't depend very much on any of its inputs, then because there's so many of them, we should see sort of an averaging phenomenon going on. Right? And so we have, of course, this is not a math statement yet, so we have to give a precise definition of what one means by being stable, right? And there's many possible definitions. We use the definition of Lipschitz, right? So we'll say that f is sigma Lipschitz. Right, so what does this mean? Right, so what is the definition of f being Lipschitz? It means that if I take f in a point x and f in a point y, that this is smaller or equal than sigma times the distance between x and y, so the north, right? So if the input doesn't change very much, right, then the function cannot change very much either. Right, and then what the theorem says, it says that this concentrates very well around its mean. In particular, it says that the probability of f of g being very far away from its mean, bigger than t, that this is right, that this is smaller or equal than something that we've seen many times, right? Is always 2 exponential, and then you get minus t squared over 2 sigma squares. Okay, so it says that if f depends on the dependency that it has on its parameter is very stable in this sense, then it needs to be close to the mean in a very specific way. Okay, so here I will not show the proof of this. I'm going to point, because this is the kind of proofs that is easier read. So I'll point to the notes for the proof of this, and in the notes, basically, I proved this with the worst constant. Not a 2, but something, I don't know, maybe it was, maybe pi over 2 or pi or something like this. But it's, the proof is a lot simpler with the worst constant. And the proof is actually very nice. There's a very nice trick on it. So I recommend taking a look at the notes for the proof of this. With a different constant. So what we'll see now is, let's see an example of this, just to get a feel for what this is saying. So of course, a very nice example to try is a function that, we've seen a lot, and depends very little in each one of its inputs, which is the average, right? So if you take f to be the average, okay, let me see if I can keep as much as possible here. Okay, let's say that f, okay, let's give an example. Let's say f is the average. Average function. Okay, so what I mean by this, right? F of g is just g1 plus gn over n. Right? Another way to write this is this 1 over n g transpose Bool's vector. Okay, So let's see what kind of Lipschitz constants this has. Right, so that's easy. So let's take f. Right, if we take f of x minus f of y, right, what is this? This is, right, we can push the 1 over n outside even. Right, what do we get? We get 1 transpose x, right, we get 1 transpose x minus 1 transpose y. So this is 1 transpose x minus y. Right, now we can use Cauchy-Schwarz. Right, we have an inner product, so we get 1 over n, norm of the whole length vector, norm of x minus y. Right, the norm of whole length vector is square root n, so this is equal to 1 over square root n x minus y. Right, so f is 1 over square root n Lipschitz. Right, and now we can see what the inequality gives us, right? We can just plug it in. Right, and if it's a mean, right, the mean, right, on average, I mean, the expected value of the mean is, of course, 0, so it tells us that the probability, okay, I wanted to use another color. Right, it tells us that the probability, right, that the sum of, or say the 1 over n of the sum of the GIs, and the probability that this is bigger than some t, right, is smaller or equal than 2 exponential of, and now we get 1 minus t squared, right, this gets 2, so 2 and n up here, right, which is exactly what we know. If we take, we usually don't see it with the 1 over n here, right, so there would be an n that go into the t, and you would make a 1 over n squared show up here in the change of variables, and so the n would move down here. This is exactly the inequality that we know from Gaussians and from just standard concentration inequalities. Maybe the right quantity to look at would be not 1 over n, but 1 over root n, so that this is a standard Gaussian, and then this change of variables of that root n on the t would basically take this n away. Right, so this is one example where from this general result of Gaussian concentration, we can recover, things that we've seen before. Now, it's worth pointing out that, of course, here we're working with Gaussians, but there's essentially concentration results of this type for many types of random variables, not necessarily Gaussians, just satisfying different properties, and f maybe instead of being Lipschitz satisfies also other things. And so even inequalities that are not on the control of the expected value, things are not Gaussians, can still translate into tails using very similar type of techniques. For example, say Lagrange concentration, and so on. But so what we're doing now is I'm going to show you an example using Wigner matrices so that you see the kind of thing that one can obtain directly from expected control of expected value of norms and the Gaussian concentration. Okay, so let's move to Wigner matrices. Okay, so let's say we have W as Wigner matrix. Okay, so this is an n by n symmetric matrix where the entries are Gaussian. Wij is just a Gaussian. Right, 0, 1, and on the diagonal you can put variance 2. I mean, it doesn't really matter, but they are symmetric. Right, so Wij is equal to Wji. That is important. Okay. And so now we're going to get a tail, a control on the tail of the spectral norm of W. Right? We want to control things like what's the probability that the expected value, what's the probability that the spectral norm of this matrix is bigger than something. But we're going to do it through a bound on the norm, on the expected value of the norm. Right? So you saw from the homework actually that the value of this expected value is smaller or equal than 2 times root n. right? This can be proven using selective comparison. This was one of the problems in the problem set. Okay? So now from this, we're going to actually be able to get control on the tail of the random variable of the spectral norm of the Wigner. Right? Why? Because right, we should think a function that goes from, you know, we'll think of f. Okay, I'll use a bit of abusive notation of f of g as the norm of the Gaussians. Right now, the abusive notation is the fact that, you know, the Wigner matrix has a bunch of Gaussians in the entries. That's how I'm populating G, right? So maybe but I'm not just saying f of w because w has the same entries on the upper half and the bottom half. So maybe I should say on the upper is a function of the upper triangular parts of w, right? And gives a spectral norm of w. And let's show that this is Lipschitz. Okay, that's easy, right? So let's say that I have two matrices W1, right, and W2. Do this, right? W1 and W2. And let's say that we want to control the difference between their spectral norms. Okay, so if we have something like this, then we know by triangular inequality or just by thinking about what the spectral norms are, right, that this is for sure smaller or equal than the spectral norm, the difference between the spectral norms. Right? So now, if, right, you can just prove this for this and the other one with triangular inequality, you can just think of what it is that the norm is, right? Here you're taking the maximum in each one of these, while here you can take the maximum over just one time the maximum. Now, right, so here we have the spectral norm of these two matrices, but we also know that the spectral norm is bounded for sure by the Frobenius norm. The spectral norm is just the largest eigenvalue in absolute value, while the Frobenius norm is the sum of squares of them. So this is bounded by the Frobenius norm of these random variables. Right, but now the Frobenius norm is right. The Frobenius norm is basically the L2 norm of the entries, right? And so this is essentially, you know, this is essentially the L2 norm. So L2 norm of entries, or is exactly the L2 norm of entries, and so therefore is essentially the L2 norm of the G of the upper diagonal part. There's just a square root of 2 factor because things are showing up twice. So this is a proof if you track exactly what the symmetry does, f is square root 2 Lipschitz. Okay, so f is square root 2 Lipschitz, this is essentially the proof, right? The absolute value of the norm of the differences of f are smaller or equal than this is the L2 norm of this, the L2 distance of the entries, and each entry shows up twice, not the ones in the diagonal, but the other ones, then this gives the square root of 2. Right? And I mean, in the diagonal, oftentimes we normalize the diagonal to have variance 2, and this would also give the exact same square root 2, even on those entries. Okay, so then if we have that, that is square root of 2, then Gaussian concentration, right? Gaussian concentration gives immediately something, right? Because it gives immediately that, you know, the probability that let's say that we're right, because we only have an upper bound on this. Let's say that we're only interested in understanding the upper side of the inequality, right? The inequality will say that typically the spectral norm of W is very close to the actual expectation, but here we're only interested really in, because we only have an upper bound here, we're just interested in understanding the tail of it being potentially too big, right? So if we have something like this, right, the probability that W, right, is bigger or equal than expected value of W plus T. Right, then this, by Gaussian concentration, will be smaller or equal than exponential of minus T squared, and then over 4, which is, you know, the 2 plus the Lipschitz constant square. Okay, and we use here the fact that right, this bound, we haven't used that bound yet, but we will now. Okay, so let's say that we have this. What does this mean? Right, using that, we really have that the probability that the spectral norm of W is bigger or equal than 2 root n plus t, right, is now smaller or equal than exponential of minus t squared over 4. Okay, so we already transformed this into a tail bound. But the nice thing is that we're actually transforming this into a very, very strong tail bound, because let's see what this gives, right? So if we do this, it's symmetric. Right, so let's say that we take, for example, right? For example, let's take t to be 2 square root log n. Right, let's say that t is equal to 2 square root log n, then what do we have? We have that the probability, right, of the spectral norm of W being bigger or equal than 2 root n, which is its typical size, plus 2 square root log n, which is tiny in comparison, is smaller or equal than what we get here, exponential of minus 4 log n over 4, so exponential of minus log n is exactly 1 over n. Right, and so we see that as the dimension grows, right, we see this super, like, really strong concentration phenomenon, is that the probability that it even deviates, right, that the size of 2 root log n is way smaller than 2 root n. The probability that it deviates from its expectation or from the value that is typical is actually really, really small. Right? Even a tiny deviation already has a probability of 1 over n. Right, and so that's why we'll focus actually on controlling. We'll focus for the rest of this lecture and this couple of lectures, we'll focus on inequalities of this type. Because from inequalities of this type, using either Gaussian concentration or other types of concentration, we'll be able to get tail bounds. Right, and then in the references there'll be pointers to exactly how to get those tail bounds, but now I want to understand controls of this type, because these proofs will help us understand a bit better what's happening with matrix concentration.